Before us we see the historic city of Edinburgh, with its formidable castle perched on a volcanic plug and located strategically in the estuary of several Scottish rivers, including the River Forth. Parts of Edinburgh are listed as UNESCO World Heritage Sites. There are over 4,500 listed buildings within the city, a higher proportion relative to area than any other city in the United Kingdom. Edinburgh is encircled by a green belt, designated in 1957 to contain the outward expansion of the city and to prevent the agglomeration of urban areas. However, this green belt has already been encroached on by suburban areas and developments such as Edinburgh Airport. Such urban expansion is not unique to Edinburgh. 54% of the world's population lives in urban areas, a proportion that is expected to increase to 66% by 2050. Urbanisation, combined with the overall growth of the world's population, could add another 2.5 billion people to urban areas by 2050, with close to 90% of the increase concentrated in Asia and Africa. We are seeing an often rapid and uncontrolled growth of cities. Especially in developing countries, area-wide information about quickly changing megacities is rare. Especially in developing countries, area-wide information about quickly changing megacities is rare. Industrialised countries suffer from urban sprawl and the consumption of their green areas due to a predilection for development with single-family houses, induced by improved living conditions. Urban monitoring can be defined as the extraction of urban footprints or more detailed urban land cover mapping. It also includes monitoring of the urban topography through digital surface models. Urban footprints are the spatial extents of urbanised areas. The areas dominated by buildings, streets and impervious surfaces, i.e. man-made structures, natural surfaces within cities are not taken into account. A map of urban footprints is therefore a binary settlement mask with only two classes, urban and non-urban, commonly derived by remote sensing data. Multi-temporal settlement masks enable quantification of urban growth or shrinkage. Mapping urban footprints is of fundamental importance. The global spatial distribution of urban areas is a key element of sustainable development. It is also required for regional scale planning. Often remote sensing derived maps of urban footprints are the only source of information on the extent of cities, especially in developing countries. Urban land cover mapping provides information on the type of natural and artificial objects covering the Earth's surface. It is not to be confused with land use, which describes human activity on the Earth and the manner in which land cover is used. Accurate land cover maps are needed by city planners who require efficient methods for management of large urban areas. Remote sensing data helps to provide regularly updated area-wide land cover information. And SAR data in particular offers a potential for automated mapping of urban land cover. A digital surface model, or DSM for short, describes the elevation above sea level of the ground and all features on it, while a digital terrain model, or DTM, describes only the ground elevation above sea level. Normalized DSMs can be derived by subtraction of a DTM from a DSM, with the result that they contain only heights of objects on the surface. DSMs of urban areas are important for city planners, commercial services and research. They are required, for example, to quantify solar insolation for photovoltaic plants, for telecommunications, to provide viewshed information for estate agencies and tourism, for flood modelling, for damage detection, and for improved urban area mapping. SAR is very suitable for urban footprint and urban land cover mapping. This is primarily due to the characteristically high backscatter received over urban areas due to the predominance of double bounce scattering. Such double bounce scattering from the many right-angle corners found in urban areas efficiently reflects the microwave signal back to the SAR sensor. Strong returns also come from metallic objects such as bridges, silos and utility poles due to their high dielectric constants. Another factor which makes SAR suitable for urban area mapping is the stable nature of anthropogenic structures, which leads to high interferometric coherence between SAR acquisitions. Using threshold values for backscatter and coherence, it is possible to extract urban footprints. SAR is sensitive to roughness, but the definition of a rough or a smooth surface varies as a function of the SAR wavelength. The use of multiple wavelength SAR can therefore provide more information on textual variations necessary for land cover mapping. Further information for urban footprint and urban land cover mapping can be provided by different SAR polarizations. For example, where surface scattering is present, such as in the case of concrete man-made structures, the light polarized components dominate. Where volume scattering is present, as in a forest canopy, the cross-polarized components reflect strongly. Multipolarized SAR data can therefore provide useful additional information for urban area mapping. As with different wavelengths and polarizations, the backscatter of urban areas also changes with varying instance angles. Small instance angles yield a poor range resolution. This may result in small urban units going undetected. But large instance angles cause longer radar shadows, which may conceal urban land cover, especially if there are high buildings. The instance angle range between 40 and 45 degrees is considered the best compromise for urban area mapping. Urban digital surface models can also be derived from SAR data. Typically, this is done through interferometric techniques, which calculate the phase difference between two or more SAR acquisitions separated by small perpendicular baselines. These techniques work where there is high coherence. They may not work if there is too much vegetation interspersed in the urban fabric, contributing to loss in coherence. The leafy city of Edinburgh may be challenging to map within SAR, but at least from this vantage point, modern construction has not yet obscured the historic urban fabric. Let's hope that remains so.